Now my signal is very stable. Internet.
हम्म।
नया मॉडेम लगा गया ना.
ओ अच्छा।
4 gigahertz.
ओ।
All right. All right. So let's discuss this moving coil galvanometer. पहली बात तो what is a galvanometer? You remember that? It's a device to check whether there is a current in that branch or not.
यस सर, हाँ।
So it's for detection of small currents. It's not meant for measurement per se. It is only meant for detection. Okay. This is and what is the principle being used is what you do is you make the current pass through it. जो भी current आपको नापना है वो
हम्म।
current इसके थ्रू जाएगा और अंदर जो वो रेक्टेंगुलर लूप है, okay,
हाँ।
उस रेक्टेंगुलर लूप से जब करंट जाएगा तो वो रेक्टेंगुलर लूप that is kept in a magnetic field. So a uniform magnetic field is established by the use of this magnet, and this loop, as soon as it gets a current, starts rotating. And when it rotates, what you do is you put a spring-like structure which is here. ये spring-like structure दिख रही है?
हाँ, दिख रहा है।
So if it rotates, it also एन एंटी क्लॉकवाइज, मतलब जिस भी डायरेक्शन में ये जाएगा तो स्प्रिंग विल रेजिस्ट द मोशन. अगर आप इसे घुमाओगे तो एक ऐसी जगह आ जाएगी जहाँ पे स्प्रिंग जो है वो इसको एक पॉइंट पे आके रोक देगा. तो स्प्रिंग ऑल्सो अप्लाइज अ टॉर्क ऑन इट. So
हम्म।
one torque is coming on it from the torque produced by the current coil lying in a magnetic field. और नीचे उसको रोकने के लिए there is a spring-like mechanism. Okay. So the torque which is provided by the spring, okay, this spring is called as restoring torque.
ओके।
Okay. It is very similar to linear situation. If you have a spring like this, अगर आपके पास एक ऐसा spring है and if you pull this string, अगर आप खींचते हो spring को तो the spring wants to come back, right?
हम्म।
So it's a restoring. It wants to come back to its initial position. Similarly, this spring, अगर आप इसे connect करोगे torque with the moving coil, this is a moving coil. Okay, the moving coil is a rectangular frame which you see. So that torque on that will also rotate the spring क्योंकि वो connected है यहाँ पे. They're connected.
ठीक है।
So a point will come where the spring will balance the torque provided by the magnetic field.
हम्म।
So at that point we will say equilibrium has been attained. Okay, so the coil will no longer move inside the magnetic field. वो हिलना बंद हो जाएगी वहाँ पे.
हम्म।
Okay. At that point you will note the measurements and what you will say is that the torque which is coming from the current in a magnetic field, we have already studied this, was given by, if you remember, force into force arm. Force into force arm. So the force is BIL,
करेक्ट।
right? And the magnetic field which is there is B. I is the current in the rectangular loop, L is its length. Multiply it with the perpendicular, okay, which is the width of the loop. इससे multiply कर लो. So that will become your force arm. If you remember, यहाँ पे collinear force थी, तो they were cancelling. The torque was getting produced because of this. ये collinear थी. There was no perpendicular gap. यहाँ perpendicular gap है. Right, so the perpendicular gap is the width. So let's say the
ठीक
width
है।
is this. The length into width is area. So this is BIA for a single turn. But if there are multiple turns, you will get BINA Newton meter. So that's your total torque on the rectangular loop. So this torque has come because of the current in the rectangular loop.
Hmm.
But the rectangular loop is connected to a spring which also gets twisted, and therefore it exerts a restoring torque. स्प्रिंग अपनी नॉर्मल सिचुएशन में है, लेकिन वो अब ऊपर से उसको आप मरोड़ रहे हो ना, ऊपर से यू आर जस्ट
हाँ.
ट्विस्टिंग
Yes,
इट.
sir.
So that will it will resist this, and it will say I want to go back to my, so it will apply what is called as a restoring torque. Okay, and that restoring torque which is provided by the spring, okay, is T restoring. It is proportional to the angle by which the rotation has been produced. Okay, it's proportional to that. तो आपकी coil अगर यहाँ पे थी, if the coil was like this, and due to rotation it has moved through a certain distance, okay, and this is the angle by which it has rotated, so this is the angle, the
Hmm.
angle by which the uh, rectangular loop has twisted is same as the angle by which the spring has got twisted. So a point comes where the torque inside the spring, which is this, okay, this is a torque in the spring, this is constant of proportionality. So this theta I'm representing is that theta where the restoring torque becomes equal to the torque which got generated because of the current carrying conductor. Current carrying conductor, the torque is fixed
Hmm.
because B is fixed, current is fixed, number of turns is fixed, area is fixed. So the torque which is getting produced in the rectangular loop is fixed, whereas the torque in the spring is adjusting in nature. It keeps on adjusting itself depending on how much twist is coming from the upper side. And a point comes where the spring then says, okay, now my restoring torque has become equal to the torque on the rectangular loop, and therefore BINA, which is the torque on the rectangular loop due to the magnetic field, is balanced by the torque coming from the spring down
Hmm.
below.
Hmm.
And then the coil stops moving further. No more motion is there.
Okay.
And therefore you can measure theta, which is B magnetic field, current flowing, NA divided by K. Okay, where K is called the torsion constant. Okay, these are not complicated constants.
Hmm.
This K which was introduced as a constant of proportionality in the expression of torque applied by the spring, K is called as a torsion constant of the spring.
ठीक है.
Okay, in linear motion, when you have spring like this and you want to calculate the restoring force, अगर आप इस मास को ऐसे खींचोगे F, तो यहाँ पे जो restoring force आती है वो होती है kx,
Hmm.
where x is the amount of change in length of the spring when you pull it by a force F. थोड़ा spring लंबा हो जाता है, so वो जो लंबाई एक्स्ट्रा आई है वो है x, and k is called as a spring constant. रोटेशन के केस के अंदर when you are rotating the spring because of the rectangular loop, when the spring gets twisted, we don't use the word spring constant, we don't use kx is used when it's a linear pull, सीधा खींचने पे. जब आप इसे
ठीक है.
रोटेट कर घुमाओगे, जैसे बोतल के ढक्कन को घुमाते हैं, if it's a rotational case it is called as a torsion constant. So it is basically what? It is the amount of torque produced per angular motion. It is a fixed quantity for a given spring. So you can keep on changing springs you will get a new torsion constant. Every spring will have its own T. Obviously, depends on what material, etc., you're using.
Hmm.
Okay, so which means now your torque produced by the current, which is BINA, has got balanced by a torque coming from the spring. Right. So this is your situation, and therefore you can see the rotation which has happened in the coil is given by this formula. ये formula है उसका. So what you do is you connect this coil with an external scale. ये coil आपकी. Do you see these lines?
Yes, sir.
This is a top view of the coil. ऊपर से ऐसे नजर आ रही है coil. Okay, it has some width also ना.
Hmm.
तो ये ऊपर से देखो ये तारें लिपटी हुई हैं. वो किसके ऊपर लिपटी हुई हैं? They are on a soft iron core. A soft iron core has very high permeability, mu.
Hmm.
So it allows the passage of magnetic fields from the magnet very nicely. And you can see the magnets are also very special type. Now, word about the construction. The magnets are, if you notice, something like this. Circular. What they produce is something called as a radial magnetic field. It is not like this. Normally you would draw like this, right? Like this, straight.
Okay.
बट ये मैग्नेटिक फील्ड ऐसा नहीं है. इसके अंदर इन्होंने इसको कर्व बना दिया, सो दैट व्हाट यू गेट इज अ radial magnetic field. The good thing about radial magnetic field is wherever the coil moves, it finds a uniform magnetic field. I will tell you how, but for the time being, this is a radial magnetic field which is being used, not like this. ये नहीं यूज होता, रेडियल वाला होता है. और जो वायर कनेक्टेड है इसके साथ, जो ये पॉइंटर है, जैसे जैसे कॉइल घूमती है वैसे वैसे स्केल भी बाहर हिलता है. एंड यू कैन सी द रीडिंग ऑन द स्केल. मोर इज अ रोटेशन, मोर राइटवर्ड, मतलब और इधर चला जाएगा ये, तो स्केल में मूव हेयर. द मोर करंट यू मे पास, because you can see from the formula that the rotation is proportional to the current. N of a galvanometer is fixed. Number of turns. एक बार खरीद लिया तो खरीद लिया.
हाँ.
A of the galvanometer is fixed. खरीद लिया तो खरीद लिया. साइज एरिया आ गया, खरीद लिया. जो अंदर मैग्नेट है that is also fixed. K is also fixed, which means the physical part of a galvanometer construction is the number of turns inside the galvanometer, the area of the coil you're using, and the magnetic field and the torsion constant of the spring. तो ये तो construction हो गई उसकी.
Correct.
If you play with this construction, you can change things about galvanometer. For example, if you keep a very low torsion constant, then for the same current your deflection will be very high. कि अगर आप बहुत छोटा ले लोगे torsion constant, right?
अच्छा.
Then you will have to have a very high deflection to balance out the external torque. If K is very small, deflection बहुत ज़्यादा करनी पड़ेगी, तब जाके एक restoring torque निकलेगा. अगर K बहुत बड़ा लिया आपने स्प्रिंग का, तो स्प्रिंग बहुत दमदार होगा, वो थोड़ी सी डिफ्लेक्शन में ही काफ़ी टॉर्क पैदा कर लेगा.
समझ गया.
If you buy a galvanometer with very high K, the K is very very high, then it can provide you a very strong torque with the current. Immediately it will stop your rotation. You will get a very minor deflection. But if you buy a galvanometer with low torsion constant, which means then for the same current this will go very high. बहुत ज़्यादा टर्निंग के बाद वो टॉर्क मिल पाएगा, क्योंकि टॉर्जन कांस्टेंट इज वेरी स्मॉल एंड द टॉर्क प्रोड्यूस्ड is equal to k theta. if K of a galvanometer is very low and you want the same torque, क्योंकि करंट वाले कॉइल को रोकने के लिए तो टॉर्क जो आना है वो आना ही है,
हाँ नहीं है हाँ।
लेकिन अगर आपने छोटा K ले लिया तो थीटा बहुत बड़ा करना पड़ेगा टू बैलेंस इट आउट,
हम्म
क्योंकि रिस्टोरिंग टॉर्क तो चाहिए ना हमें. इट विल कम फ्रॉम वेयर? इट विल कम फ्रॉम द स्प्रिंग. द क्वालिटी ऑफ द स्प्रिंग विच इज प्रोवाइडिंग इट इज K.
हम्म
नंबर ऑफ टर्न्स आपने बढ़ा दिए
हाँ
खरीदते वक्त. So you can see the deflection is proportional to number of turns, right? If you have very high turns in the galvanometer, compare a galvanometer with everything is same, but the number of N1 is greater than N2. The current is same, everything is same, but the number of turns in the first one is very high. You will find the more the turns, the more is the deflection shown.
हम्म
एरिया सेम रख लो, मैग्नेटिक फील्ड सेम रख लो, नीचे रीस्टोरिंग टॉर्क के लिए जो टॉर्जन कांस्टेंट है सेम रख लो. कंपेयर टू galvanometers with different turns and you can see current is also current going inside them is same. Since you have more turns inside the uh, galvanometer, the overall rotational torque will go up, isn't it?
हाँ agreed.
Bina will increase.
हम्म
The Bina will increase. The torque goes up drastically.
हम्म
Now you have to stop that torque, which means the spring will need more phi to generate more torque. ज़्यादा घूमने पे ज़्यादा restoring torque आता है ना. Torque is
हाँ
proportional to theta.
agreed.
If you, for example, have two galvanometers, everything identical, but one galvanometer has a very strong magnetic field,
हम्म
right? So if it has a very strong magnetic field, it will apply more torque on the rectangular loop.
understood.
If it applies more torque on the rectangular loop, then the spring below will have to turn more to produce the equivalent restoring torque. स्प्रिंग को मेहनत ज़्यादा करनी पड़ेगी. स्प्रिंग की मेहनत दो तरीके से हो सकती है. या तो स्प्रिंग का टॉर्जन कांस्टेंट बढ़ा दो और थोड़ी सी डिफ्लेक्शन में वो ज़्यादा टॉर्क पैदा कर ले. लेकिन अगर आपने टॉर्जन कांस्टेंट सेम रखा है दोनों गैल्वानोमीटर के अंदर और एक में मैग्नेटिक फील्ड ज़्यादा लगा दिया है, तो फिर बराबर टॉर्जन कांस्टेंट होने की वजह से हाउ विल यू जनरेट मोर रिस्टोरिंग टॉर्क? द ओनली वे टू डू इज बाय इंक्रीजिंग द एंगल ऑफ डिफ्लेक्शन.
Yes sir.
The one with more magnetic field in it has a coil experiencing more torque from the magnetic field, and therefore the spring will have to work hard, which means the spring will generate more phi, more rotation,
हम्म
right? So these are, so if they ask you about what is a construction and all that, you can explain all of this.
ठीक है.
Okay, all right. Now one thing which we noticed was that the galvanometer had a uniform radial magnetic field. Okay,
Okay.
there is a cylindrical soft iron. You can see the cylinder shaped soft iron core. Cylinder means this.
हम्म
This is a cylinder, right?
correct.
और coil इसके ऊपर आपने ऐसे लपेट दिया. एक टर्न, सेकेंड टर्न, थर्ड टर्न, ऐसे, right? So this is the turns. So many turns are there, right? So why are you doing this? Because the cylindrical soft iron core is an excellent medium for the magnetic field to pass through it. If you keep air, आप बोलते हैं कि I will not use iron core, I will use air instead. You can decide कि I will just have a frame with no, but if you have iron, then your magnetic field wants to pass through iron, not through air, because the
Yes.
permeability
हाँ.
of the iron core is very good. It allows magnetic field flux to pass through it very nicely,
Hmm.
right? So you are going to get a very nice magnetic field without much wastage.
Understood.
Okay, so there is a cylindrical which not only makes the field radial, so this particular cylinder, if you notice, is also supporting the radial nature of the magnetic field. It is also
Hmm.
like exactly identical to the external magnetic field shape.
Understood.
Okay, since the field is radial by design, we have taken sine theta is equal to 1. So wherever the, see, generally what happens if you have a situation where, let me just write it. If you have a coil like this, and what you do is you apply a magnetic field which is straight like this. Okay, journal case, right?
Hmm.
And this is where the beauty of radial will come. So this is your magnetic field. If you rotate this by a certain amount, then an angle comes between the coil and the magnetic field. Right? The
Understood.
torque was also given by mu cross B. And the torque was also given by Bina sin theta actually. How is that
Hmm.
हमारा sin theta change हो गया रोटेशन में? We should, अगर रोटेट होता तो sin theta भी आना चाहिए फिर.
हाँ हाँ आना चाहिए.
लेकिन वो आता नहीं है यहाँ पे. रीजन क्या है? What you have done is your magnetic field is radial. So आपकी coil अब rotate होके मान लो it has come here.
Hmm.
Wherever your coil goes, it will find that the magnetic field is always having a theta which is equal to 90 degrees with the mu
Hmm. हाँ.
in any direction. कहीं भी घुमा लो क्योंकि वो magnetic field की जो direction है, it actually is this radial.
Okay.
So if your coil is now like this and your magnetic field is radial,
Hmm.
तो mu यहाँ पे है,
हाँ.
राइट? और ये आपका मैग्नेटिक फील्ड ये रहा 90 डिग्री. तो
Okay.
जहां भी ये घूम के जाता है, वेर एवर इट गोज, इट फाइंड्स की कोई ना कोई मैग्नेटिक फील्ड और इसके म्यू के बीच में देर इज अ 90 डिग्री कनेक्शन.
Okay.
It can rotate anywhere it wishes to. कहीं भी चले जाओ. Wherever it will go, it will find a magnetic field where the magnetic field direction and the angle between the magnetic dipole is 90 degrees.
Hmm.
So the radius was deliberately kept so that nowhere there is a compromise on the torque. नहीं तो torque, if you remember, was variable. It was bina sin theta.
Yes, sir.
So torque kept on varying with theta, but suddenly we have, irrespective of wherever the coil rotates, the torque is bina sine 90. Right, so if they ask you why the radial magnetic field is chosen for moving coil galvanometer, your answer is straightforward. One, obviously, uh, the angle between the magnetic field and the mu is always 90 degrees.
Yes, sir.
That is why you have chosen a radial magnetic field, because you're working with maximum torque irrespective of position of the coil. You're not working with a variable torque in the case of a moving coil galvanometer. You want the torque to be constant throughout uh, the the region in which the coil is operating. The torque, there is no angle that comes into picture.
Hmm.
ठीक है? This is one. Okay. So obviously you can see that more is the deflection, more was the current.
हाँ, yes sir.
राइट, अज्यूमिंग आपने एक बार डिसाइड कर लिया, तो अगर आप करंट बढ़ाओगे तो डिफ्लेक्शन बढ़ेगी, क्योंकि अगर आपने जो टॉर्क ड्यू टू करंट है, मैग्नेटिक फील्ड है, वो बढ़ जाएगा और आपके जो स्प्रिंग को नीचे ज़्यादा मेहनत करने के लिए ज़्यादा रोटेट करना पड़ेगा. ओके, नाउ यू कैन यूज अ गिल्वानोमीटर इन नंबर ऑफ वेज. One way to use this is to use as a detector to check if the current is flowing in. ये तो पता चल ही जाएगा, डिफ्लेक्शन होते ही पता चल जाएगा there is a current.
Yes sir.
Right? We have come across this usage और Wheatstone bridge में भी, if you remember, in the Wheatstone bridge also, right? We had used the central arm branch for detection of current.
Correct.
Right? We had kept a galvanometer here, and then we had studied the meter bridge. Okay, so Wheatstone bridge also helps you measure the same thing, which is detection of current in the central branch. Okay. All right. So if you keep a galvanometer here and there is no deflection, right? So we saw usage of galvanometer in the Wheatstone bridge. It was used for detection of current.
Hmm.
Right? Now, galvanometer cannot be used exactly as an ammeter, okay? Ammeter is different because ammeter is only used for measurement of current. Exact value, not detection. Detection means pass हुआ था कि नहीं हुआ था current, that's all.
Agreed.
Measurement means exact value of current क्या है वो बताना है. Now, there are two reasons why you cannot use. Galvanometer is very sensitive. Okay? It gives a full-scale deflection for a current of order of few microamperes pass through it. क्योंकि इसको बनाए इस तरह से गया है कि जरा से करंट पे भी ये मूवमेंट दिखा दे. ओके, तो ये the moment very small amount of currents pass through it, which is to the order of microamperes, mu a, it shows a deflection. एमीटर का ये काम नहीं होता कि वो थोड़े से ही करंट पे हिल जाए. एमीटर का काम है जितना भी करंट गुजर रहा है उसको पूरा नाप लेना.
अच्छा.
4 एम्पियर है तो 4 एम्पियर को नापना है. जबकि गैल्वानोमीटर की कंस्ट्रक्शन ये है कि थोड़ा सा भी करंट पास करो, डिफ्लेक्शन हो जाए बस. It is too sensitive. An ammeter is not designed to be sensitive.
ठीक है.
For measuring currents, the galvanometer has to be connected in series and it has to have a very large resistance. This will alter the value of the current in the circuit. To overcome these difficulties, one attaches a small resistance RS called as shunt resistance in parallel with galvanometer, so that most of the current therefore passes through the shunt. So what they do is, if you directly keep a galvanometer in a circuit, if you're given a circuit and you directly put a galvanometer like this, right?
Yes sir.
This is one way to keep your galvanometer. The second way to put a galvanometer is to use it properly to reduce its sensitivity and put a resistor in parallel with galvanometer. तो galvanometer जो है सो है, और जिस सर्किट में आपने नापना है current, now you're converting your galvanometer into an ammeter. The way to do this is, whatever current you have to measure comes in because you have applied a very small shunt resistor here. This current, small, so most of the current, for example, 5 amperes come here. Now
ठीक है
5 amperes, see that there is a shunt resistor here, and the shunt resistor is very low. So most of the current passes here. Because current always wants to go through the path of less resistance. And some current then passes through this. Okay. So what you have to do is you have to, if you want to convert a moving coil galvanometer into an ammeter, you just need to connect that galvanometer with a shunt
right
resistance. And this is the resistance of the galvanometer itself.
हम्म
This is the resistance of the shunt. And generally the galvanometer resistance is very large as compared to the resistance of the shunt.
okay
Okay. I'll just show you how, why then this becomes a ammeter. Now, measurement कैसे हो रही है फिर? Okay. It's because our ultimate goal in an ammeter is not deflection, but measurement. Okay. Let's define one more terminology before we reach there. Now, so there is one resistance which is the galvanometer resistance, and then there is a parallel resistance to it, which is a very small value called as shunt resistance, and together they are called as the ammeter. दोनों हम मिला के ammeter बना लेते हैं ये. Okay. One more term which you have to know about this is that now, because a ammeter has to have a good scale, so you need to do a calibration of the scale. कि कितने करंट पे वो कितनी रीडिंग दिखाएगा, क्योंकि स्केल में if there is a scale, you have like this, right? So एक स्केल मूव करने में पॉइंटर अगर यहाँ पे है और एक ही मूवमेंट कर रहा है वो, राइट? 1 यूनिट मेजर कर रहा है. So we have
yes
to
sir
first prepare the galvanometer as an ammeter by connecting a shunt, and then we have to use a laboratory for the calibration of the ammeter. Okay, and then we do marking on it to read the current value. And all of this is done in a laboratory setting. That just a thermometer also has readings.
yes sir
Somewhere you have to do a clear ना कि this much mercury movement will be called as 1 degree. तो यहाँ पे mark कर दो. 1 degree पे यहाँ पे निशान mark कर दो, right? All that graduation and the calibration is done in laboratories. Okay.
understood
Now we don't need to get into detail of how the practical work is done. We define the current sensitivity of the galvanometer is the deflection you get per unit current. So the phi is the deflection in degrees or radians divided by the current. So for every 1 ampere, how much deflection will it show? Or maybe for 1 microampere. Maybe if you pass 1 microampere, it moves by a distance of 0.5 degrees. Then you
okay
can do a marking there. ये 0.5 degree का motion है. That means 1 microampere current has moved. If 10 reading is coming, then that means the radians or degrees which are covered is 0.5 into 10. 5 degrees have been covered. So the pointer has moved by 5 degrees. And for half a degree, it shows a current of 10 raised to power minus 6. For half a degree, it shows 10 raised to power minus 6. So for 5 degrees, it will show how much. How much will be the current, right? So you can do a ratio proportion. So first of all, in the laboratory, you will decide the sensitivity of your galvanometer. For 1 microampere, I would like to have a deflection of 0.5 degrees. So make your N, A, B, and K accordingly when you go to the market and manufacture a galvanometer. Work on your turns, area B, K, and depends on the market need also. Some
yes sir
people may ask you, we don't want microampere, yeah, we want to measure only amperes. So give us a galvanometer which for one deflection, one one deflection only, marked like this. Second is here, third is here, fourth is here, fifth is here. So that's your scale, right?
Huh.
We want that you measure 1 ampere for one deflection. We don't want micro,
Understood.
right? So you will accordingly decide कि okay, so you will, okay, I will make this 15 degrees. और जितने भी आपके आ रहे हैं, depending on the construction, and then we'll start marking equal, and they say for every 15 degrees moved, the deflection of 15 degrees, the current being measured is 1 ampere. उसके बीच का current हमें चाहिए ही नहीं. We don't
Yes,
want to
sir.
measure 4.5, which means we don't want this to be a very highly sensitive ammeter. The more sensitive it is, the more smaller current will produce the same deflection. If you microampere से 1 degree move होता है और 10 raised to power -3 से भी 1 degree move होता है, तो ये वाला जो ammeter है, this is more sensitive because
Hmm.
it is capable of moving 1 degree for every 1 micro ammeter, whereas this one can only move 1 degree with 1000 times the current.
Much.
So you have to, as a manufacturer, decide what sensitivity you want, and to control sensitivity, you can control N, because size of the galvanometer is very difficult to control, right?
Yes, sir.
I mean, how can you vary? कभी बड़ा तो एक आपने साइज तय कर लिया तो आप मैग्नेट भी फिक्स हो गए आपके, स्प्रिंग भी फिक्स हो गया. द ओनली वे यू देन स्टार्ट प्लेइंग विद द सेंसिटिविटी इज द नंबर ऑफ टर्न्स, क्योंकि आप गैल्वानोमीटर को बड़ा थोड़ी ना बना लोगे. यू कैन नॉट हैव अ
हाँ.
गैल्वानोमीटर ऑफ द साइज ऑफ अ रेफ्रिजरेटर नाउ.
Yes, sir.
तो हम तो बड़ा बनाएंगे जी, इसको एरिया बड़ा कर देंगे. कांट,
हाँ, ये
राइट?
possible.
सो एरिया एक बार आपने छोटा सा गैल्वानोमीटर बना लिया, अब उसके अंदर टर्न्स ही हैं जो यू कैन प्ले विद इजीली. ईज ऑफ मैन्युफैक्चरिंग तो देखनी पड़ेगी ना, क्या इजी है.
Yes, sir.
Okay, so this is one way. You so remember the word current sensitivity. The current sensitivity is a very important term in galvanometer. Okay, it is the deflection per unit current.
Hmm.
So let's now say, can we use galvanometer as a voltmeter? You cannot.
नहीं. Hmm.
The way you convert a galvanometer into voltmeter is first attach this resistance of the galvanometer with a very high resistance wire. Remember, voltmeters are kept in series
Hmm.
with the circuit.
Yes, sir.
Sorry, in parallel with the, ये voltmeter always it is in parallel with the,
अच्छा. Hmm.
right, so that no current goes through it. So you need a very high resistance. Now, galvanometer doesn't have that higher resistance. Therefore, you add more resistance to it from outside. Yeah. And now the same galvanometer has become a voltmeter with very high resistance. So whatever current comes in, least loss happens here. Most of the
Understood.
current should pass through this, not through this, because this can be thousands of ohms.
Hmm.
The current would not like to pass through a place where it finds high resistance,
Understood.
right? And remember that voltmeter is different from potentiometer, because potentiometer draws no current. It works on the principle of balancing the potential with the help
Hmm.
of its potential gradient, V by L.
Yes, sir.
Whereas voltmeter will disturb the circuit. थोड़ा current ले लेगा ये.
Hmm.
Right? So voltmeter has a disadvantage, but voltmeter is used, it is available, it is cheaper, easy to connect and all that. Right? कहीं भी उठा के ले जाओ. Potentiometer कहाँ का लेके जाओगे आप?
हाँ, वो possible.
Right? Cumbersome. So voltmeter will disturb some reading. So if the voltage here actually was 200 volts, it may measure 190 volts. It may measure 180 volts. It may measure, maybe 198, depending on how good it is. There is a loss, and loss generally tolerable losses are 1%. 200 volt नापने निकले थे, 198 ही नाप पाए. So that is acceptable. It's a good galvanometer. Sorry, voltmeter. If you have a voltmeter which is 200 volts, but ends up measuring it 200 volts as 180. It's a very bad voltmeter.
Hmm.
10% की variation loss दिखा रहा है, right? So it is drawing too much current. So whatever voltage is available for the actual work done, 10 volt, 20 volts is going to this, and 180 volt is also going. तो measuring device खुद ही circuit की 20 volt voltage ले गया, which is not a good thing,
Yes, sir.
right? So remember, in a voltmeter, you want the resistance to be of extremely high value so that it does not draw too much current. If it doesn't draw too much current, then the potential drop across the voltmeter is very low.
No.
And similarly, in the laboratory, what they do is they will again calibrate it for measuring 1 volt, how much deflection it should show. Or maybe it is capable of measuring 1 microvolt, millivolt. So decide the sensitivity. So whatever formula you're getting of sensitivity here, ये formula दिख रहा है आपको आया था deflection का. Divide both the sides by V now. So you will get the voltage sensitivity. So you can see what have they done. I by V has become 1 by R.
Hmm.
Okay, where R is the resistance of the voltmeter.
Understood.
So now when you buy or manufacture a voltmeter, the first thing as a manufacturer you need to decide is what sensitivity are you going to work on? Right? Which means how much deflection by how much voltage. Will you produce 1 degree deflection with 1 degree deflection by 1 volt? Or you're going to produce 1 degree deflection by 0.001 volt? So you're highly sensitive then.
Hmm.
Then you want to measure very small quantities, right? If you want to measure 10 volt, 5 volts, 20 volts, then you can say, okay, for 5 degrees, I will keep a voltage of 1 volt. Your reading will look like this: 5 degrees 1 volt, next 5 degrees 2 volts. So your deflection is coming from the pointer. वो तो degrees में ही हिलता है ना.
Hmm.
और ये आपकी हो गई 1 volt because phi is proportional to voltage. That calibration you have done that conversion in the laboratory. How many degrees are equivalent of how many volts? So how much is the sensitivity has been decided. Maybe there is a Galvanometer voltmeter like this with a lot of calibration. It has 100 markings on it.
Hmm.
And each marking is 1 volt. So this can measure up to 100 volts. Right? So this is angle, right? ये deflection. Pointer तो
हाँ.
यहीं से आएगा ना. Pointer 0 पे था, हिल के 20 पे चला गया. So when you buy a voltmeter, you will notice this is mentioned on the voltmeter. The voltage sensitivity, the rating of the voltmeter.
Hmm.
If you again want to control the voltmeter's sensitivity, play with the number of turns.
अच्छा.
और क्या करोगे? What else can you do?
Hmm.
साइज बदल जाएगा ना. टर्न्स ही हैं जो बिना साइज बदले हुए लपेटते जाओ और काम हो जाएगा.
हाँ. Yes.
So if you double it, you can double the sensitivity.
समझ.
Sensitivity means for 1 volt, how much deflection is going to happen. That is broadly sensitivity.
Hmm.
हम कितने डिग्री को हिला रहे हैं इस पॉइंटर को. For 1 volt, for every one. If you're measuring very small, then maybe 1 millivolt. 1 millivolt is capable of producing how much? 5.
Understood.
Okay. So conclusion is If you want to convert a galvanometer into an ammeter, sorry, a galvanometer into ammeter, use a shunt with the
Okay.
resistance of the galvanometer and put
Hmm.
ammeter in the series in the circuit, because ammeter should get all the current it has to measure. So therefore it has to be put in series.
Hmm.
If you put a voltmeter in series, the resistance of voltmeter is so high that it will change the current of the whole circuit. If you put
अच्छा.
voltmeter, which is a very high resistance, in series, then the high resistance of the voltmeter will get added to the resistance of the circuit,
Hmm.
which you don't want. You don't want to disturb what is being measured,
Yes, sir. हाँ.
right? So always put voltmeter in parallel to the element across which voltage is being measured. To
Hmm.
convert a galvanometer into ammeter, use a series resistance with galvanometer and increase its voltage, sorry, resistance very high, so that when it is connected in parallel to any circuit or any branch, it does not draw too much current. ठीक है?
Yes, sir.
All right. Give me 1 second. Let's write some maths behind this now. Okay, which is this conversion we have just learnt. How do we actually express that conversion numerically? जो हमने सीरीज में लगाया था ना, वैसे तो कुछ भी नहीं है, सीरीज और पैरेलल है, there is nothing in it. But let's see
Hmm.
in the case of how do we actually tackle it. Okay, so we will do some practice on that in the form of some numericals. All right. So assume you are given a rectangular coil. So practice question number 1. So we are doing practice on ammeter, galvanometer, and voltmeter. Okay. So you have a rectangular coil of area, which is the area of the rectangular loop, to be 5 into 10 raised to power minus 4 meter square, and n is given to be 60. Okay, and the coil has a radial horizontal field, radial. Okay, so your B is also given to you, which is 90 into 10 raised to power minus 4 Tesla, and you are given that if you pass a current of 0.20 milliampere, if this is a current that you pass, the phi you get is 18 degrees. एंगल तो दिखता है ना लेबोरेटरी के अंदर.
हाँ.
Okay, you have to find the spring constant. So it's okay, no problem. I know that the torque which got produced from the external magnetic field is this much, and it will be equal to the restoring torque which is coming from the spring. Okay, so this is coming from spring. So K, which is your torsional constant of the spring, will be, and remember there is no sine theta, nothing, sine 90 हर जगह पे, because it's a
Hmm.
radial given in the question. So B is radial, right?
Yes, sir.
Put the values and you will get B is so okay. So sometimes you will be given cos. So cos is 10 raised to power minus 4 Tesla. हमें टेस्ला में लेना है, मैं गॉस में नहीं लेना होता. ये कन्वर्जन याद रखनी है आपको.
Hmm.
Okay, so B is given, I is given, N is given, A is given, and phi is given. So you will get, if you notice, this is the unit. ये तो पूरा टॉर्क है, ये न्यूटन मीटर. ये भी न्यूटन मीटर ही है.
Hmm.
सो यू आर कैलकुलेटिंग के, तो फाई नीचे चला गया, तो न्यूटन मीटर के नीचे क्या आ गया? डिग्रीज आ गया.
Yes, sir.
सो दिस इज द यूनिट. सॉल्व इट एंड यू विल गेट द आंसर. ठीक है?
ठीक है.
Alright. So let's say now, let's do another question. Okay. Alright. So if you have a situation where you want to play with the sensitivity of the instrument, same thing, everything will be same. Now what you will be given is, please tell us the sensitivity of the equipment. So if you're given the number of turns, you're given the area and all of that, what you will do is, if you have to calculate, for example, ऊपर वाले केस में अगर करंट सेंसिटिविटी की बात करें हम,
Hmm.
ओके, सो करंट सेंसिटिविटी कितनी आ रही है अगर आप ध्यान से देखो, हाउ मच करंट सेंसिटिविटी इज देयर? It is 18 degrees divided by 0.20 milliampere. ठीक है? So if we solve it, this will be 180 upon 2. So this will be 90 degrees per milliampere. Correct?
Yes, sir.
फॉर्मूला तो पता ही है ना. सेंसिटिविटी इज व्हाट? सेंसिटिविटी इज नथिंग बट द डिफ्लेक्शन प्रोड्यूस पर यूनिट करंट. सो हाउ मच डिफ्लेक्शन पर यूनिट करंट, मिली एम्पियर में रख लिया मैंने. ओके, सो फॉर एग्जांपल लेट्स सी, यू हैव अनदर केस. फर्स्ट गेट फ्रेंडली विद द बेसिक्स ऑफ, सो एक there is a galvanometer which has for example 100 divisions on the
Hmm.
scale, and you, what you do is you get a if you uh, it reads maybe 500 millivolts for a full deflection. Question is, what is its sensitivity? So sensitivity is the uh, Vs. Okay, so if you notice, one division जो है, it amounts to how much? That is the question, right? So 100 divisions can measure, can measure 500 millivolts. So one division will measure how much? This much.
Hmm.
ये क्या आ गया? 5 millivolt per division. राइट? तो वोल्टेज सेंसिटिविटी कितनी हुई? वोल्टेज सेंसिटिविटी का क्या फॉर्मूला देखा था हमने? डिफ्लेक्शन डिवाइडेड बाय वोल्टेज.
Hmm.
सो 100 divisions are moved by 500 millivolts. So 1 by 5. So 5 millivolt will make one division move. डिवीजन भी एक्चुअली होता तो एंगल ही है ना, बट कई बार वो एंगल नहीं लिखते उसको. ये एक डिवीजन हो गई ना, यहाँ से यहाँ तक. कई बार लिख देते हैं ये ए, हो सकता है 2 डिग्री हो, बट कई बार सिर्फ डिफ्लेक्शन वर्ड यूज होता है. Got it?
Yes, sir.
Okay, so just minor words are there. Get friendly with the words so that when the real numerical comes, you can easily handle it. All right. Let's say Okay. 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 Now, one more thing which you have to understand. Okay. For example, in the case of conversion of galvanometer into voltmeter. Okay. So how do you do this finally, right? ठीक है, series में resistance लगा देते हैं, right? So you have a RG and you connect it with a very large resistance R. Convert हो गया. But how do you decide the
हम्म
value of R finally? See, R की value decide होती है how much voltage is to be measured. ठीक है, वो अगर आपको मैं बता दूं कि the voltage I need to measure is so and so,
ओके
right? That means I tell you what is the capability of voltmeter I need. फाइनली वोल्टेज ही नापनी है ना आपने.
हम्म
तो कैपेबिलिटी मैं आपको बता देता हूँ. तो मान लो आपके पास एक वो है गैल्वानोमीटर पड़ा हुआ है जो 25 माइक्रो एम्पियर्स नाप लेता है. ओके. शुरू में तो आपको गैल्वानोमीटर ही मिलेगा, राइट? सो लेट्स से the resistance of the galvanometer is 25 ohms, and the sensitivity of the galvanometer is 50 microamperes. Okay, this is the sensitivity. And what is this? Resistance of the galvanometer. अब किसी ने बोला please convert it to a voltmeter which is capable of measuring 10 volts.
हम्म
ठीक है. बोला जी ठीक है जी, वोल्ट मीटर में कन्वर्ट करना है इसको. सो वोल्ट मीटर में कन्वर्ट कर रहा हूँ मैं. एंड व्हाट इज द कैलिबर आई नीड? 10 volts. Now remember, the resistance of the galvanometer is there and it has a sensitivity, and we know that the resistance has to be connected in series for this conversion,
हम्म
and this has to be of a very high value. So it gets connected to some circuit and you want to measure 10 volts, right? यहाँ कोई रेजिस्टेंस होगा, आपने वोल्ट मीटर लगा दिया. गैल्वानोमीटर के साथ आपने एक हाई रेजिस्टेंस वैल्यू लगा ली. तो ये जो
हम्म
टोटल इंस्ट्रूमेंट है ये बन गया आपका वोल्ट मीटर. पैरेलल में लगा दिया सर्किट के और आपको वोल्टेज नापने को बोल दिया 10 वोल्ट्स.
ओके
भैया 10 वोल्ट तक नापने के लिए मुझे यूज करना है इसको. तो लोग बोलेंगे ना कन्वर्ट करने के लिए बताओ जी वोल्टेज कितनी लगाओगे फिर. ठीक है.
ठीक है
So how do you do this? What you do is you say my total resistance of voltmeter is Rg plus R. Okay, which means it is 25 plus R.
हम्म
ये तो आपने एक्सटर्नल लगाया है. वोल्टमीटर का रेजिस्टेंस आ गया आपका. ठीक है.
हाँ
और आपको निकालना है व्हाट इज दिस रेजिस्टेंस ऑफ द एक्सटर्नल ये. नाउ सी द करंट sensitivity which is given to you, right, is basically alpha upon I, deflection per unit current. So what you do is, और आपको नापना कितना वोल्ट है? 10. So 10 volt is equal to the current sensitivity multiply by 25 plus R. So this is microamperes. So this is 10 raised to power minus 6. ये कट गया और ये कितना आ जाएगा 10 raised to power 6 divided by 5 is equal to 25 plus R. So this is 1 million divided by 5, which means how much is it? 1 million divided by 5, 2 lakhs.
हाँ
Right. So you convert this, and really speaking, the 25 ohms will make no difference in a 2 lakh.
हाँ यस सर
क्या फर्क आ रहा है इसके अंदर? तो you just say this is ignorable. So my resistance which I am going to add. तो resistance कैसे निकला है? Resistance निकालने के लिए external के लिए आपने basically क्या करा है? Whatever voltage is to be measured, you have divided it with what? The current sensitivity. This gives you the external resistance that you need to apply.
ठीक है
अब अगर मैं आपसे बोलूं, if I apply 5 volts to this instrument, okay, same instrument है जो 10 वोल्ट तक नाप सकता है,
ठीक है
राइट? ये तो पता चल गया है कि ये 50 माइक्रो एम्पियर ले रहा है, राइट?
यस
ये
सर
दोनों यही तो लिखा है मैंने, ओम्स लॉ जैसे ही तो लिख दिया है,
हाँ
I into R, right? So question is, the 5 volts is applied. Is the reading coming on the voltmeter? What do you think was the current? 10 वोल्ट पे कितना करंट गया था? सेंसिटिविटी थी 50 इंटू 10 रेज़ टू पावर माइनस 6, तो 5 वोल्ट पे इट विल बी हाफ,
यस सर हाँ ठीक है
है ना?
हाँ
Okay. So you have to basically just calculate this value, and for example, if you use this voltmeter and say apply say somebody says, okay, I want to measure half volt with the help of this voltmeter, okay, half volt. उस केस में कितनी आएगी आपकी रीडिंग? भाई आपने 25 माइक्रो एम्पियर भेजा था तो 5 वोल्ट्स थी, तो 1 वोल्ट पे आपकी कितनी आ रही है रीडिंग?
फाइव
5 माइक्रो एम्पियर्स, और हाफ वोल्ट पे कितनी हो जाएगी? 2.5
2.5
माइक्रो एम्पियर चाहिए आपको, राइट?
यस सर
So this is okay, let's convert now a galvanometer into an ammeter. Now first question you will ask that person is, I want him to okay, you want me to use my galvanometer as an ammeter, but tell me भाई ये कितना करंट नापना है तेरे को? He will say, I want to measure a full scale deflection which I want to measure is 1 amperes. That's my goal.
अच्छा
जैसे वहां मेरा गोल था 10 volts नापना, similarly I have a goal of measuring 1 ampere. तो मुझे गोल मालूम चल गया और मुझे मालूम है कि मुझे ये सीरीज में ही लगाना पड़ता है.
हाँ
So I put a RG and a shunt resistance. लेकिन ये खुद पूरा का पूरा इंस्ट्रूमेंट तो सर्किट के साथ सीरीज में ही लगता है.
सीरीज में हाँ
So this is my overall R ammeter, right?
करेक्ट
And this is R shunt. So RG and RS have come together, and you know how much is the total current you want to measure. ये भी आपको गोल मालूम है बड़ा clearly. और इन दोनों का पैरेलल टोटल रेजिस्टेंस विल बी ओम्स लॉ R1 मतलब RG into RS divided by RS plus RG, R1 R2 by R1 plus R2 पैरेलल में है क्योंकि दोनों
यस सर।
nothing great about it, right? Straightforward है ये तो बिल्कुल ही. Now what you do is, so they are in parallel. So remember, if they're in parallel, the voltage across both of them is common, right? So whatever current is coming, you want that this should be able to measure total of 1 amperes. So you cannot send a current of more than 1 ampere anyway. It is
ठीक
not
है।
capable. You have already decided कि इससे ज़्यादा current I will not allow it to pass. Okay. Now, once the current enters of 1 ampere, and you know the sensitivity of this galvanometer, which we chose, was 50, right?
यस सर।
So 50 microampere इधर चला गया और
हाँ।
ये है अपना 1 एम्पियर. तो जो गैल्वानोमीटर है यहाँ, सॉरी ये तो शंट है, शंट में चला गया 1 एम्पियर माइनस 50 माइक्रो एम्पियर. ये बहुत छोटा नंबर है. क्या लिखें इसको? ठीक है.
ठीक है।
So दोनों both are in parallel, so the voltage across both of them is same. So RG into 50 into 10 raised to power minus 6 is equal to शंट का रेजिस्टेंस जो निकालना है multiply by this much. दोनों parallel में है तो voltage V is equal to IR is same in both the cases. Ohm's law. Right? Calculate the value of the shunt resistance and it has to be very small. जो भी आएगी 10 raised to power minus 3 ohms. Decimals में होगी, बहुत छोटी सी वैल्यू.
ठीक है।
Got it?
यस सर।
So this is the way conversion is done.
अच्छा।
Just give me 1 second. Any doubts in your mind so far?
नहीं सर।
ये क्वेश्चन आता है, जेई में भी आएगा, बोर्ड में भी आएगा.
अच्छा।
The focus of the question is understanding sensitivity first. If you understand sensitivity and how to put it in these, the way I've just told you, this is the only way, or there is no other method. First, for board purpose, you know the construction of galvanometer, why radial, why there's that restoring torque, torsion constant, and all of that. वो तो हो जाएगा आराम से. The second part, which is the conversion, is the slightly tougher and tricky. But उसमें भी conversion में कुछ है नहीं if you know how to use sensitivity. Your goals are clear. मेरे को आप conversion के लिए voltmeter में बोल रहे हो, मुझे total voltage बताओ क्या नापनी है. मुझे ammeter में convert करने को बोल रहे हो, मुझे total current बता दो जिसपे maximum deflection आएगी.
ठीक है।
And you get the answer. Go and practice this. Come with your doubts now.
ओके सर।
I will send you an assignment. Assignment, I mean, you already have ample questions in SLA, but my questions will be bit MCQ types.
समझ गए।
वो जो मैं MCQ भेजता हूँ, please do them. It will make your base on a daily practice basis very strong. Once you will get accustomed to appearing for JEE mains. पर आपके फंडे भी बहुत clear हो जाएंगे. You will come to know a lot of new things.
ठीक है।
ठीक है? So I will ping you when I'm back. Hopefully I'll ping you by 1:30, 1:45 and let's have the class.
अच्छा।
What time is your chem?
3।
Is it there today?
यस सर।
अच्छा आज है. Okay, then see if you can manage. Otherwise we will meet in the evening.
इवनिंग में मतलब पॉसिबल है, जैसे अब तो काफी दिन हो गए नहीं हो पाई।
हाँ
मतलब आप ले पाएंगे इवनिंग में?
हाँ मैं ले पाऊंगा, but I will let you know the time. I think a good time. I can do late also, by the way. I don't know what time do you get free late.
या तो ऐसे कीजिए, अगर आप 4 बजे ले सकते हैं तो।
यार आई ऑलरेडी हैव अ क्लास फ्रॉम 4 to 5:30 आई एम booked.
एंड 6।
Booked.
अच्छा, तो फिर लेट नाइट ही ले लेते हैं यहाँ पे
वो
फिर।
बेस्ट रहेगा बिकॉज यू विल ऑल्सो बी रिलैक्स्ड.
ठीक है, तो
बट
लेट
करते हैं,
नाइट ले
लेट्स डू अ
लीजिए।
2 hour क्लास ऑफ मैथमेटिक्स.
ठीक है, लेट नाइट कर दीजिए।
ठीक है, कर लेते हैं. यू कैन भी कर लेना, यू हैव योर डिनर एंड ऑल दैट, चिल
हम्म।
आउट, देन यू
ठीक है।
सिट विद मी एंड वी विल जस्ट प्रैक्टिस.
ठीक है, 10 to 12 कर लेते हैं, ठीक।
चलो ठीक है.
हम्म।
सी यू इन द नाइट देन. बाय.
बाय सर।
टेक केयर.